Alright, well what we'll do is go through this last review packet. I'm having some issues with recording this, so if I stop it abruptly, I will get started on another one. Alright, so anyway, we have a certain gas sample here with a temperature changing from 275 to 320. So what I'll do is write temperature 1 is 275 K and temperature 2 is 320 K. So right away you want to think the temperature is changing, so we're going to use some form of the combined gas law. So it says the new volume of the gas is 5 liters, and then what is the original volume of the gas? Alright, so what we're going to use is Charles's law, V1 over T1 is equal to V2 over T2. The thing you want to remember though is your temperatures have to be in Kelvin. Now they're already in Kelvin, so we're in good shape there. So we don't know V1. Temperature 1 is 275, V2 is 5, and temperature 2 is 320. So when you do the math there, you can cross multiply and divide. You should get a value of 4.3 liters. So you should notice that this is Charles's law, and that it's a direct relationship between volume and temperature. Alright, let's move on. Let's see if this switches. Alright, I'm going to have to do it this way. So let me switch to a new. Let me clear the screen, and hopefully we'll be in business here. Alright, so number 2 says what's the pH of a 0.015 molar HCl, and that probably should say solution. So HCl we know is an acid, and it's an acid because it produces that hydrogen ion and the chloride ion, but it's the hydrogen that we care about. So if our original concentration here is 0.015 molar, since this is a strong acid, that's going to be 0.015 molar also. So according to our equations, pH is equal to the negative log 0.015, so when we do the math there we should get 1.82. And that should make sense because HCl is an acid. Acids have pHs less than 7, so that makes sense. Alright, moving on. Let's whoops. Alright, let me clear the screen and get my pen back. Alright, so number 3 says what's the concentration of a solution of sodium hydroxide that has a pH of 10.18. So we're talking about sodium hydroxide here. So that's a base, and it's a base because it produces that hydroxide ion. So if our base has a pH of 10.18 and we want to know the concentration of this solution, if we know the concentration of the hydroxide, then we automatically know the concentration of the solution. To find the concentration of hydroxide, we're going to use this equation to the negative pOH. So we need to know pOH. Well, as we know, pH plus pOH is equal to 14, and we know our pH, so we just have to subtract that from 14, and we get a pOH equal to 3.82. So if we take 10 to the negative 3.82, finish off the math there, you're going to get 1.51 times 10 to the negative 4th, I believe. Yep, that's a 4. Okay, so let's move on to the next one while this thing is working well. Okay, let's get a pencil. Alright, now this problem is a little bit goofy because in years past we've talked about weak bases. So I'm going to do this problem as if this were just a base. And it is a base, but normally we have that hydroxide present. So what we're going to do is start with 0.5 grams of NH3, and we're going to convert that to moles. So we have 17 grams per mole. And if we do the math there, we get 0.029 moles. Well, we need a concentration, so we're going to divide by our volume, and we're going to convert that to liters, which would give us a concentration of 0.196 mole per per liter. Now, since this is a base, what we're going to do is just assume that the concentration of OH is equal to 0.196 molar. Now, technically, that's not right at all, but again, we're gonna treat this like it's a strong base. So, if we want to know the pH of that solution, we're going to find the pOH first by taking the negative log of our concentration, which would give us a pOH of 0.708. And then if we subtract that from 14, we would get a pH equal to 13.3. And that should make sense because bases have pHs greater than 7. And again, for those of you who are watching this who know about weak base calculations, yes, that is not the way you would technically do this. Alright, so let's move on. Let me move the screen down a little bit. So we are looking to do, alright, so, sorry, a little bit of a delay. So let's clear that and get my pen back. Alright, so the next one says, what is the boiling point of a solution with 34.3 grams of the ionic compound dissolved in that much water? So first of all, you would need to know the Kb for water is 0.56. So what we're going to do is take 34.3 grams of magnesium nitrate, and we're going to convert that to moles. So I'm going to add up the molar mass here, and I'm going to get 148 grams per mole, and that's going to give me 0.232 moles. So we're going to use our formula. Delta T is equal to Kb times molality, which is moles of solute, over kilograms of solvent times I. Now the college prep students, don't worry about this I, you're just going to do this and this. So our delta T is going to be equal to 0.56, 0.232, I might be developing some pen issues, so I might have to stop this soon. 107 kilograms. And if our I value is going to be 3, since this is going to produce 3 ions, and that is going to give us a delta T equal to, it's actually going to be 3.3. So our new boiling point, we would add that to 100, and it would be 103.3. I'm going to stop this video here because I'm developing those problems. So I will continue this one on the next video.